September 26, 1983. Just after midnight, deep inside a secret bunker south of Moscow, an alarm starts screaming. On the giant screen in front of him, one word appears in bright red letters: launch. The early warning system has detected a missile, not a drill, not a test. A live launch from the United States, heading straight for the Soviet Union. The man staring at that screen is Lieutenant Colonel Stanislav Petrov. He has about 15 minutes to decide whether this is real. If it is, protocol says he must report it up the chain of command immediately, triggering a process that could end with a retaliatory nuclear strike. If he's wrong, and he reports it as real, he could start the very war the system was built to prevent. If he's wrong the other way, and he stays silent while missiles are actually inbound, he leaves his country defenseless in the opening minutes of a nuclear war. Then the screen updates. Not one missile, 5, an entire wave, according to the machine sitting in front of him, that is only ever supposed to detect the real thing. Petrov has minutes to decide, and the fate of hundreds of millions of people rests on whether he trusts a machine or his own gut. To understand how one man ended up holding that decision in his hands, we have to go back to how this system came to exist in the first place, and what almost impossibly delicate piece of engineering it depended on. By the early 1980s, the Cold War had turned nuclear weapons into a matter of minutes, not hours. Intercontinental ballistic missiles could cross from the United States to the Soviet Union in around 30 minutes. Submarine-launched missiles fired from closer range could do it in a fraction of that time. That left almost no time for humans to verify an attack the old-fashioned way, by waiting to see explosions on the ground, or waiting for a second wave to confirm the first wasn't a fluke. So both superpowers built early warning systems designed to catch a launch the moment it happened, using satellites that could watch for the heat signature of a rocket engine igniting thousands of kilometers away before the missile had even cleared its own launch silo. The idea behind this kind of system is called launch on warning. Rather than waiting to absorb a nuclear strike and then retaliating with whatever survived, each side wanted the ability to launch its own weapons the moment an incoming attack was detected, so that a first strike couldn't simply wipe out the other side's ability to respond. On paper, this made both sides safer because it removed the incentive for either country to attempt a surprise knockout blow. In practice, it meant that an enormous amount of trust had to be placed in machines built to detect an attack in its first few seconds, using signals that were, by their very nature, faint, distant, and easy to confuse with something else. The Soviet system watching for this was called Oko, meaning eye. It used a constellation of satellites positioned in highly elliptical orbits, so that for long stretches of their orbit, they hung over the northern hemisphere, staring down at American missile fields at a shallow angle close to the curve of the Earth. This geometry was deliberate. By looking across the Earth's limb rather than straight down, the satellite could see a missile's engine plume silhouetted against the black backdrop of space, rather than against the bright, cluttered daytime ground, where a rocket's heat signature would be far harder to isolate from ordinary background noise. This was considered a major improvement over ground-based radar, which could only detect a missile once it had already climbed high enough to clear the horizon, by which point a large fraction of the available warning time would already be gone. But building a sensor that can reliably tell the difference between a missile launch and literally anything else that produces a bright flash of infrared light viewed from thousands of kilometers away through the edge of the atmosphere turns out to be a genuinely brutal engineering problem. The sensor isn't looking at a video feed a human can glance at and immediately recognize. It's measuring intensity within a specific infrared wavelength band above a specific brightness threshold in a specific region of the sky and translating that into a binary judgment, missile or not a missile. A rocket engine in powered flight produces an intense, narrowband infrared signature as it burns fuel. hot enough and bright enough to stand out clearly against the cold vacuum of space. That's the entire premise the detector is built around. But infrared light doesn't come stamped with its source. A sensor tuned to catch that narrow band of wavelengths can't inherently distinguish a rocket plume from any other object radiating or reflecting light in that same band if the intensity and geometry happen to line up closely enough. The system has no concept of a missile. It only has a number, a threshold, and a decision rule that fires the moment that number gets crossed. On this particular night, the satellite's sensors were staring at the edge of the Earth just as the sun began climbing over the horizon on the other side of the planet, and its light was catching a rare, high-altitude formation of clouds above Montana. Right in the field of view, Oko was watching for American missile fields. To the satellite, sunlight bouncing off ice crystals at just the right angle, at just the right altitude, produced an infrared signature that looked, by every measurable criterion the sensor was built to check, exactly like the heat plume of a missile in powered flight. This is the exact same category of failure the very best sensor systems still struggle with today, distinguishing a genuine signal from a coincidental one that happens to look identical from a distance, using nothing but a handful of numerical thresholds. The satellite wasn't malfunctioning in the sense of a broken part or a wiring fault. It was doing precisely what it was built to do: detect infrared light above a certain threshold, in a certain wavelength, in a certain part of the sky. It just so happened that a natural phenomenon at that exact moment produced a signal that checked every one of those boxes at once. Back in the bunker, Petrov doesn't know any of this yet. All he knows is the system, built by some of the country's best engineers and tested rigorously for years before being put into service, is telling him a missile has launched. And then within about a minute, it tells him again, and again. Within roughly 4 minutes of the first alert, the display shows 5 missiles inbound. Here's where the mechanics of the decision start to matter as much as the mechanics of the sensor. Petrov's job that night wasn't actually to build early warning technology. It was to interpret it and to decide what got passed up the chain. He was one of the duty officers responsible for monitoring Oko's output and reporting it to senior military leadership, who would then decide whether to authorize a retaliatory strike. In the Soviet military's mental model of how a war would begin, an American first strike was expected to be massive, not 5 missiles. If the United States wanted to cripple the Soviet Union's ability to retaliate in one blow, doctrine assumed they would need to launch hundreds of missiles simultaneously, overwhelming any possible response, not open with a small, almost tentative first wave that would do little more than announce the attack was coming. That single detail, the discrepancy between what doctrine expected an opening strike to look like and what the screen was actually showing him, became the crack that let doubt in. 5 missiles didn't fit the shape of the attack everyone had been trained for years to expect. And underneath that doubt sat something harder to quantify: pure engineering skepticism. Petrov wasn't just a soldier standing watch. He had trained as an engineer and had helped work on parts of the early warning infrastructure himself. He understood, at a level most duty officers on shift that night might not have, exactly how many independent things had to go right for that system to be telling him the truth, and exactly how many different ways it could be fooled by something that wasn't a missile at all. He also knew ground-based radar hadn't yet independently confirmed anything. Radar could only pick up an inbound missile once it rose high enough to clear the horizon. And by the time the satellite alert came through, nothing had shown up yet on any radar screen. In theory, that gap made sense on its own. The missiles, if real, simply hadn't traveled far enough yet to be visible from the ground. But it also meant Petrov had exactly one source of information telling him the world was ending, and 0 independent confirmations from any other system, anywhere in the country's defense network. Every second that passed without radar confirmation added a small amount of uncertainty to the picture. Every second closer to the theoretical arrival time of an actual missile, subtracted from the time available to make a decision at all. This is the part of crisis engineering that almost never gets talked about. It's not just about whether a sensor is accurate, it's about how a human being is supposed to act rationally while a clock they can't stop and can't slow down is actively running out in front of them, with consequences that scale into the hundreds of millions of lives. Petrov picked up the phone to the duty officer's station and reported that this was a false alarm, not because he had proof, because he made a judgment call based on incomplete information under a level of time pressure that very few people in human history have ever had to operate under. And he chose to bet that a machine was wrong rather than trigger the beginning of a nuclear war. He would later describe running through the decision almost mechanically in his head. Radar showed nothing. Doctrine expected an overwhelming first strike, not 5 missiles. The system was new enough that its failure modes weren't fully understood, even by the people who built it. Weighing all 3 of those things against each other in the span of a couple of minutes, he decided the odds favored a false alarm. If Petrov had passed the alert up the chain as a confirmed launch, standard procedure from that point would have moved into the hands of senior Soviet leadership, who would have had their own extremely short window to decide on a retaliatory strike, working from the exact same flawed data Petrov had just chosen not to trust. There is no way to know for certain what would have happened next, whether senior command would have shared his skepticism or acted immediately. But multiple military historians who have studied Cold War launch protocols on both sides consider this one of the closest documented moments the world has come to an accidental nuclear exchange. Now here's the part of the story that puts the fear back into it. Petrov's gut instinct was right, but right afterward the system flashed the alert again, because whatever confluence of sunlight, cloud formation, and satellite geometry had triggered the first false detection was still happening, moment to moment, in the sky above Montana. The exact same conditions were still present, which meant Petrov had to make the same decision with the same incomplete information more than once in the span of a few minutes, each time knowing that being wrong in either direction carried a catastrophic cost, and each time with slightly less time on the clock than before. This is a useful moment to pause on what's actually happening from a systems design perspective. OCO wasn't a poorly engineered system. In fact, on a technical level, it worked exactly as specified. A threshold of infrared brightness was crossed at the correct wavelength band in the expected geographic region, and it correctly flagged that as a detection, precisely as its engineers had designed it to do. The failure wasn't in the sensor, it was in the assumption, baked into the entire warning architecture, that a positive detection from a single source was sufficient grounds to escalate toward a nuclear response. Nobody who designed OCO intended for one satellite's reading, unconfirmed by any other source, to be the sole trigger for judging whether a nuclear war had begun. But in the moment, under real-time pressure, with an alarm blaring and a word in red letters on the screen, that's functionally what the system was asking Petrov to accept. This exposes something that shows up again and again in high-stakes engineering. The gap between a system working correctly and a system being trustworthy are not the same thing. A sensor can perform flawlessly, exactly as its engineers intended, and still produce a signal that is functionally indistinguishable from the very disaster it was built to detect. Reliability and accuracy are not the same property. OCO was reliable. On this particular morning, it was not accurate. And the only thing standing between that gap and a nuclear war was a single human being deciding not to fully trust a machine that had never given him a documented reason on paper to doubt it. What makes this moment even more unsettling is the broader climate it happened inside of. September 1983 was, by almost any measure, one of the most dangerous single months of the entire Cold War. Just 3 weeks before Petrov's shift, a Soviet fighter jet shot down a civilian airliner, Korean Airlines Flight 007, after it strayed into Soviet airspace, killing everyone aboard and triggering a wave of international outrage and diplomatic accusations that pushed relations between the two superpowers to their lowest point in years. Soviet leadership at the time was also increasingly convinced, based on intelligence assessments that turned out to be badly mistaken, that the United States and its NATO allies were actively preparing a surprise nuclear first strike. That fear would reach its peak just weeks later, in November of 1983, during a NATO command exercise called Able Archer, which simulated the lead-up to a nuclear conflict in such realistic detail that some Soviet officials reportedly worried it might be cover for a genuine attack. In other words, Petrov wasn't making his decision in a calm, neutral environment where a false alarm could be shrugged off as an obvious glitch. He was making it during the single tensest stretch of paranoia either side had experienced in decades, when the argument for assuming the worst and escalating immediately was, by the political climate of the moment, entirely reasonable. Sponsor segment placeholder. Radar confirmation never came. No missiles struck. 23 minutes after the first alert, the theoretical impact window for those 5 Phantom missiles passed, with nothing hitting Soviet soil. Petrov's judgment had been correct, and the entire episode, from the first alarm to the moment the danger passed, had lasted less than half an hour. In the aftermath, Petrov wasn't given a medal. He was reprimanded informally for failing to properly document the incident in his logbook in the required amount of detail, because in the chaos of the moment, filling out paperwork wasn't exactly his top priority. He was also, according to those who later investigated the case, quietly held partly responsible simply because a failure had occurred on his watch, regardless of the fact that his decision was the reason it didn't turn into a catastrophe. Bureaucracies, it turns out, aren't always built to reward the person who correctly ignores a broken system. He was eventually transferred to a less sensitive posting, and for years, the details of what happened that night were kept classified, known only to a small circle within Soviet military intelligence. The story didn't become public until the 1990s, after the collapse of the Soviet Union, when a retired general involved in the investigation described it in his memoirs. It took years after that for Petrov's role to become widely known internationally, and even longer for him to receive any form of public recognition, including international awards and documentaries made about the incident decades after it happened, once journalists and historians tracked him down and pieced the full story together from declassified records and interviews. Engineers who later reviewed Oko's satellite orbits identified precisely why that particular morning had produced the false alarm. The satellites were positioned to look across the Earth's limb at a low angle, specifically so they could catch a missile's engine plume against the dark backdrop of space, rather than against the bright daytime ground below. But that same low viewing angle meant that under a rare combination of solar position and high-altitude cloud cover, sunlight reflecting off ice crystals could scatter directly into the sensor's field of view in a way that mimicked the infrared signature of a rocket exhaust plume almost perfectly. Engineers subsequently adjusted the satellite's ground processing software and cross-checking procedures to require multiple corroborating signals from multiple independent sources before a launch alert could ever again reach a duty officer's screen without at least some form of secondary confirmation built directly into the system itself, rather than left entirely to the judgment of whoever happened to be on shift. Over the following years, both the Soviet and American early warning networks were gradually redesigned around this same principle. No single sensor, however well engineered, should ever be allowed to sit as the sole trigger for a decision with irreversible consequences. Redundancy stopped being treated as a nice-to-have and started being treated as the entire point of the system. This wasn't the only near miss of its kind. In 1979, an American early warning crew at NORAD received data showing a large-scale Soviet missile launch, and for several tense minutes, bomber crews were put on alert and were preparing to be airborne before it was determined that a training tape simulating an attack scenario had accidentally been loaded into the live warning system, and the exercise data had been mistaken for a genuine feed. Different failure, different country, different root cause entirely. But the same underlying lesson sits underneath both stories. Complex early warning infrastructure built to compress decision-making into minutes will eventually produce a false signal that looks exactly like the real thing. And somewhere in that chain, a human being will have to decide how much to trust it, often with no time to check twice. What ultimately saved the world that September morning wasn't a redundant sensor, or a better algorithm, or a more rigorous verification protocol. Those things came later, built specifically in response to this incident, once engineers had the luxury of hindsight and time to redesign the system properly. What saved the world in the moment itself was one engineer's understanding that a system performing exactly as designed does not automatically mean the underlying signal is true, combined with a willingness to accept enormous personal and professional risk rather than escalate on incomplete information in the 15 or so minutes he actually had to work with. Petrov himself, when later asked why he made the call, he downplayed any notion of heroism. He described it simply as being the one person in the chain who happened to understand the system's limitations well enough to doubt it, and being fortunate enough to have those particular limitations cross his mind at exactly the right moment, rather than a moment too late. It's a strange kind of legacy. The entire course of nuclear history quietly resting not on a system working perfectly, but on one person's willingness to question it when it didn't, and to keep questioning it, alarm after alarm, until the danger had passed and the sun had fully risen over an early warning satellite that for 23 long minutes had been absolutely certain the world was ending.